very nice campus. I enjoyed the campus. It's very good. Excellent. So, before I get started, just one housekeeping announcement. We are going to switch these two. Yeah, I hope you don't mind. So I will do the second post-treatment module also before lunch, and then we'll break for lunch. And I've requested this change with Dr. Manjya so that I can see some nice departments on this campus in the afternoon, right? I'll have more time to do that. Okay. I must also say that some of these modules are not very exciting for me because there is not so much research involved. So I may not take so much time talking about feedstock because I am talking about it more to just relate information. There's nothing very innovative that happens in feedstock, but you should know what is the typical feedstock, what you should be careful about, how it's made. Yeah, but maybe I'll take slightly less time for this and more time for that because I find that very exciting post treatment, right? So I hope that is also okay with you. But of course, even if I speak a little bit less, if there are any questions, I'm of course happy to answer. Let's start with feedstock for metal AM. As you know, that is our focus. We don't talk about other things so much. Yeah. So what are the two main feedstock? What two kinds of feedstock do we have for AM? Wire and powder, correct? So let's talk about both of those little bit. Let me introduce some of my colleagues here. Magnus is a postdoc, now a lecturer who works on different aspects of additive manufacturing, but mostly on titanium. Peter is from Sandvik. They are one of the biggest powder suppliers for AM. They have their own additive manufacturing cell department, and then they participate in many of our projects because whenever people make new feedstock, they need someone to test it and optimize parameters for it and publish using that feedstock so that they get better known. So Sandvik is one such partner. Ibrahim, he's a Iranian student who did his PhD with us, and now he works in the R&D department of ITW. They are one of the biggest suppliers of wires, right? So I have taken some help from them in preparing this talk. Let's start. We already spoke about that. We'll talk a little bit about powders, a little bit about wire, more about powder than wire because historically people have been using the same wires that they use for welding and cladding. There's nothing different there. Although it could change, right? Because AM is such a new field, right now people use what is available, even with standards. And that's why I find the post-treatment part very interesting because there have been standards available for materials that are traditionally manufactured for, let's say, heat treatment, and people use the same standards even now. They are specified as standards for AM, but we have shown, one of my earlier PhD students, that you need not use the same heat treatment, for example. What you can do for AM can be very different from what is traditionally done in case of cast or forged material, right? So that's important to know. Let's talk about powders in general and what are the main metal powder consolidation processes. I don't know how many of you have heard of near net shape by hot isostatic pressing. Yeah, in one sense it's a very old technology, but very prevalent in the industry. Yeah, Many of the powder metallurgy parts are made by heaping even now, or sometimes they use also cold isostatic pressing and that kind of stuff, or sintering. But uh, uh, when it comes to near net shape, this is one of the main consolidation processes in vogue, but we will not talk about that because I don't believe that uh, really qualifies as additive manufacturing. So, we take that out. Yeah. Similarly, metal injection molding also very popular when it comes to consolidating powders. Uh, so, this is just for information, it just does not fit in the rest of the things we talk about. Binder jetting, DED, PBF, we spoke about all of these, and uh, today we will talk about powders in the context of at least these two, yeah, the directed energy deposition and powder bed fusion, right. I will quickly run through, not spend so much time. If you have questions, we will spend time, but otherwise not so much. We will talk about what are the prominent methods by which powders are produced, and how, based on what is the method, how the powder properties can be different. Uh, how many of you think that these are important properties for AM? Which of these is important, which of these according to you is not important? Yeah, let's go one by one. Sphericity or shape, is it important? Yeah, why is it important? Okay, all right. Do you agree with what he said, or you have some other input? Yeah. So people generally believe that you need spherical powders because flowability is better, uh, and because you can perhaps rake it well. That's what you meant, I think, that raking is better. I will accept that. I will not argue about it at the moment, but I must tell you that powder bed is little bit different from DED because you're raking and stuff, right? So, but I must tell you that almost all of, let's say, thermal spray, right? Uh, More than half of the thermal spray powders, even more, are not spherical. Yeah, they are sintered and crushed. Yeah, therefore angular. They flow very well. Yeah, so uh, there are some things in our mind which are historical sometimes, but today we get really good powder feeders, right? We are able to feed powders which are as fine as 3 to 5 microns even, right, which earlier was not possible even with spherical powders. So, today powder feeders are very good, but by and large what you are saying is right. Yeah, spherical powders are better, uh, but you must also know that it is not absolutely necessary, right. There is uh, flowability in angular powders as well, which is not so bad. Yeah, but with powder bed, as we were briefly talking yesterday, at the moment everyone says spherical powder necessary, everyone believes spherical powder is necessary. So, we will assume that it is necessary, right, for the time being. Yeah. Size and size distribution, is that important? Why is that important? Why is size distribution important? Not much important. Who who doesn't agree with what this gentleman is saying? That size and size distribution is not important. You disagree? Why? I will say one more time. You are all engineers. Please use the right terminology, right? If size is different, you get impurities. If you say impurities, I don't like, right? So you may not get complete melting sometime. Yeah, that's what you mean, right? So that's okay. Yeah, but you can't say impurities. Yeah, yeah. Phenomena of fusion. Yeah, correct. Absolutely correct. That's the right answer, right? Having said that, uh, particle size distribution is inevitable. Yeah, it will be there, and I think that is what you were trying to tell, right? You cannot get mono sized powders. Of course you can, but you have to give an arm and a leg to get that. It will be very expensive. If you say I want powders between 10 and 11 microns or something like that, it will be very expensive, right? So typically powders have a range. We spoke yesterday about 50 to 100 microns, 10 to 45 microns. So they have a range, and that is okay. You have to live with that for any process to be practically feasible, right? Uh, and what you said also is correct. There is a lot of work done on how a size distribution improves packing density, right? So, but that's a different story. We need not get into that right now. But I'm happy you said that. For a BTech second year student, that's impressive. Yeah, that's pretty good. Yeah, powder morphology, yeah, we are for the moment assuming that you need spherical packing density, same point, right? And both of these eventually affect the bulk density of what you build. Yeah, you see all kinds of morphologies depending upon what manufacturing route you have adopted to make the powder, right? Once again, I'll go back to thermal spray. We use a lot of these kind of powders as well. Yeah, still works quite well, right? But most of the AM crowd today uses these kind of powders. Yeah, because they're afraid. Yeah, we are afraid that any other powder will not work. Yeah. So if you want to write a wish list for the kind of powders you want to buy today, here is some of the points that I was looking at on one of these websites. You want spherical shape to ensure good flow. You want particle size. It depends upon what method you are using, but let's say 50 to 100 microns. Particle size distribution should be tailored, right? I mean, if you're talking about packing density, that's not bad. If you have all of this size, you of course will not get such packing, but people say it should be tailored for the application. Nobody does that, right? Nobody does that kind of tailoring because it's just impractical. Imagine I'm a powder supplier, right? Uh, I cannot begin to make different distributions in the powder for someone who is doing DED, someone who is doing powder bed fusion, someone who wants it for coating, someone who wants it for powder metallurgy part. So the best thing they do is sieve and differentiate cut sizes, right? But beyond that, they don't do so much. But you do get, if you open any powder manufacturer's catalog, you will get many size distributions, right? Many different cuts, 5 to 15, 15 to 45, 45 to 90, more than 90, whatever, right? So depending upon what suits you best, there is a big choice to be made. Controlled chemical composition, yeah. This is where you must, who spoke about impurity, yeah. This is where you must take care of impurities, whether or not they're there, right? Controlled chemical composition. There is one aspect we will not get into here, but in some cases people expect elemental loss during processing, and therefore they want to correct that in the feedstock, right? There are many examples there. Yeah, if you expect elemental loss during processing, you have a little bit more of that element in the feedstock, and assume that it will get a little bit of it will get lost, right? So there are ways to tailor composition in that sense. some of these powders, depending upon how they are made, also have some entrapped gas in them. What happens if there is entrapped gas in the powder? Yes, that leads eventually to porosity in your build, correct? So all of these are important things to consider. Potential problems, inclusions within the powder granules. Sometimes we spoke about entrapped. Yeah, all of these you should know. You should always insist on couple of things from the powder supplier. Yeah, insist on a chemical analysis always. Yeah, insist on a size analysis as well, right? Those two things you must always insist on from whoever the source of your powder is, right? We saw this yesterday, the range of materials that you can use in AM. This is an endless list. Yeah, it can go on and on. Right now we were, while I was walking, I was talking to Dr. Manjay about what one of his PhD student does with DED, and that is multi-material. Once you talk about multi-material, I mean, the field is just wide open, right? You can do almost anything. I have a PhD student myself who's working on multi-material DED, and we are trying in that case to do in Cornell substrate with an M. Crawley and graded to yttria stabilized zirconia. So we are doing a metal ceramic functionally graded, right? So you can do anything. We have another project that we are discussing with GK and Aerospace, where they want us to build copper along with stainless steel, or copper ideally with a nickel based superalloy, and we are absolutely struggling. Why are we struggling? Take this example, copper with nickel based superalloy. Why are we struggling, you think? Huh? Thermal conductivity, I don't think that we are struggling with that so much. Yeah, I mean, mostly that. We are struggling because the laser that we have been using for depositing the nickel based superalloys suddenly is inadequate when it comes to copper. So we are not okay with that laser for when it comes to copper. So we are shopping for a green or a blue laser at this point. So anyway, that was an aside, but important that you know, there's so many things you can do. For each of these you will need powder, and you need to find suitable sources for that, right? And I suspect that each of these would, if you went back to the previous slide, how important all these issues are will sometimes depend upon which material you are talking about, okay? For example, titanium will have completely different set of challenges compared to, let's say, something like stainless steel. This will be much more forgiving. Doesn't matter if it's something happens slightly with composition, but with titanium, nickel based superalloys, your threshold is pretty stiff. Yeah, some materials like this also are extremely difficult to deal with, but here you may want to revisit the size, right? So you cannot always talk about the same particle size. These are very high melting, correct? Extremely high melting materials. So you can't use the same particle size in a given process as you would use for maybe copper or stainless steel, right? You should be aware of that. Powder manufacturing methods. Oops. You get spherical powders by ball mill anytime in your life? Huh? No, right? But yeah, if you want to mechanically alloy powders, then ball milling is a good idea, but not for spherical powders. But yeah, now that this is up, yeah, if we assume that spherical powders is our target, right? Uh, Most often people use atomization techniques, right? There are different kinds of atomization. I have mentioned some here. Gas atomization, most popular, gives you the best quality of spherical powders, not necessarily the cheapest, but best. Yeah. Uh, there is also plasma atomization, water atomization, lots of stuff there, right? What is atomization, you think? Simplest definition of atomization, anyone? Disintegration. Oh, yeah, okay.
Breaking down of a material to smallest possible size smallest possible particles.
So at the you're making life very complicated. You are relating atomization to atoms. Yeah, that's not the case. Yeah,
Particle into simplest plane. It's a single. It is sorry.
yeah, that's what I'm saying. You're relating that to atoms. That no, it's not that complicated. So usually, oh, is the problem with the projector or that cable? You think in your research or whatever you are presently doing? No, you use powders. Okay, what kind of powders do you use? Spherical. Yeah, and for what application?
Sir, HGMs.
By DED. Yeah. Okay. So you use stainless steel for DED. So when you get a powder, what do you characterize it for? Because that's something we are going to talk about here. What are the important characteristics of the powder? So what do you do with the powders once you receive from a supplier?
Sir, we do estimate, sir, to
Yeah.
check the shape size.
You will do STM, okay, for shape and size. All right. What else?
Particle distribution size.
Yeah. SCM is too much, no, for just shape and size, but yeah.
XRD.
Okay, you do that. Yeah.
XRD you do, sir.
You'll do XRD, okay. What will you do XRD
Like
for?
elemental mapping. To know the
XRD
structure, type of the structure first.
XRD for elemental mapping.
Segmental mapping basically. Basically we are determining the lattice parameter, crystallite size.
Yeah, I mean, in a more broader sense, I will do XRD to find the phase constitution. Yeah, what phases are present in my powder. Someone said EDS also. Why do you do EDS? Yeah, okay. And both EDS and XRD in some way tell you what apart from what you need in the powder is also present in the powder. So kind of impurity. Suddenly there is some oxide or some carbide or something you completely did not expect. Yeah, if something like that is present, you will get it from XRD or an EDS. Yeah, which is attached to the SCM. Right? That's very good. How about what size of powders do you get for your DED? 50 to 150. Yeah. Wow, that's big distribution. Yeah. Who else raised their hands for powder? Yeah. What do you use it for? 50 to 105. Which powder? Same. So why do you use 50 to 150 and why do you use 50 to 105? But she is also using for DED. But you can use different particle sizes. That's the point. It doesn't matter. Yeah. So you can use both. Okay now? What was the problem? Yeah, technology. Always, even in our place, we have a project meeting. More than the problems with the project, we have problems with the projector. No? So, and always hard to solve. Sometimes someone can't connect on Teams or Zoom, some crazy problem. Techniques are the most popular to make spherical powders. If you don't want spherical, there are other ways, but I've stayed out of that. Uh, Out of all these, gas atomization is the most popular, especially for powders that are used today for additive, and it involves three major steps. One is melting, the second is atomization, and the third is eventually, once you get a product, you want to size it. You want to get rid of the fines, you want to get rid of the coarse powders, right? So these are the three main steps, right? So when it comes, find a way to melt your feedstock, right? You could do it in different ways, right? You could have the charge initially in the form of an ingot. You could, if you are making complicated powders, you can put all these different powders together, make an ingot out of that, and then melt and atomize, right? And so you essentially atomize. In this case, atomization means fragmentation. Yeah, you fragment a molten droplet, not take it to the level where you can't divide it anymore and all that. That's too far, right? Atomization is fragmentation. So uh, uh, the molten stream is then fragmented, and then you cool it, right, very quickly, so that these droplets solidify really quick, and you get spherical powders. Each droplet converts into a spherical particle. That is broadly the idea in all atomization techniques, right? So the changes may really happen in how you are melting it, right? In this particular case, this is equipped with a furnace, as you can see. So the melting happens under vacuum, so that there is no oxygen pickup, etc. And then these atomized droplets that are formed because of a high pressure gas that is used for atomization, these then solidify in flight to get your individual powder particles, right? As you can imagine, these would have a very varied size distribution. Yeah, so then there is of course a collection chamber, right? So these are collected and sometimes separated using a cyclone to some extent, and then finally sieved, so that you get the kind of size cut that you require. The reason people prefer gas atomization is that it's a very clean process. You do it in vacuum. You're essentially melting a charge and resolidifying the atomized molten stream. So there is not much opportunity for any contaminants to come in, right? And so cleanliness is a big thing. Even homogeneity from a chemistry standpoint is assured, because you're just melting that stream and solidifying that. So there is no in situ reaction involved or any such thing. So you get a very homogeneous microstructure as well because of the rapid solidification. Yeah, and there are some different variants of this gas atomization, but most of the differences essentially come there, right? How do you melt this? All the difference happens there. Just like with thermal spray, as I will talk, the fundamental of how coatings form is the same. What kind of heat source you use is different. Somewhat similar here. All the differences kind of reside there, but otherwise you do get atomized droplets which rapidly solidify, cool to form powders, right? Here in vacuum induction melting gas atomization, as the name suggests, this is equipped with vacuum at the top, and of course, this vacuum during melting uh, kind of uh, ensures that it is clean. There is inert gas that is used for quenching the molten stream. So, yeah, you have different variants of that. I don't want to get too much into detail, but all of them essentially try to do the same, right? Melt uh, the feedstock. I mean, feedstock in this sense is the ingot or whatever of the same chemistry as the powder that you need, and then use an inert or inert environment to collect the powder that you desire, right? You can also do water atomization instead of gas. Yeah, use water jets like these to quench, right? Uh, this also works very well so long as water doesn't react. So, when the materials that you are producing are non-reactive, water is frequently used, it is much cooler, it gives higher cooling rates as well, right. So, how do you take a powder specimen under an SEM? Can you please tell? Little bit louder so that they should hear you.
Taken sample of a powder from the raw material tip as a piece of paper and observed under the microscope. It has time whether metallic or non-metallic we have to find it out, and then we have to place it on the carbon tape. After that we have to do the coating.
You said you take it on a piece of paper and see it under the SEM. Really, you do that?
No, sir. So in a tube, we have to first store it, sir. In a small tube.
Whether metallic or non-metallic.
Louder. I like his answer because that's what how we do it. Yeah.
Actually, we have to take the powder. First, we have to identify whether the powder is metallic or non-metallic. After that, if it is non-metallic, means we have to go for the coating.
What coating?
Normal sputtering coating.
Yeah. Mm.
Whether gold or otherwise platinum, we can use that.
Mm.
Or directly it is metallic, means directly we can place it on the carbon tape. After that, we have to use the dry air in order to fully disperse the particles throughout the carbon tape. After that, we have to place it on the SEM machine based on the what is the electron we are going to use, whether you are going to use 15 kV or otherwise 10 kV or 20 kV. Based on that, we have to perform the.
Oh, I have to go beyond coffee for you. Yeah, excellent answer, man. Very good. Did you hear everything that he said? Yeah. So that's how you test a powder under an SEM. Yeah. And how do you do elemental analysis? Right. There are so many elements in the periodic table. What do you do? Do you have an auto detector, or you tell, okay, I want to look for nickel, I want to look for chromium.
Actually, we are using Oxford instruments.
Yeah.
EDX will be the Oxford instrument. And that directly it will be analyzed, directly it will be show the elements based on what is our requirement. For example, if you are done coating, means automatically platinum will also be visible or gold will also be visible in the EDX. So we have to remove that one. Based on the requirement, we have to take that.
Very good. Excellent. Yeah. Nice. So all of you are now experts in SEM characterization of powders for AM. Yeah. But good answer. We should talk during tea break. I'm scared if you take it on a piece of paper. I'm very scared. I'm scared for your SEM more than anything else. Yeah. So I think we are losing a little bit of time here. So yeah, long story short, all of them do almost the same thing. Two things can vary. How are you melting the material? How are you cooling the material? Those are the two things that vary, right? Mostly. Here people use a plasma for atomization, and then you can cool again with these plasma torches are very high power, right? But this was one of the more innovative ways to do that. Uh, you will also come across something called prep powders. How many of you have heard of prep? Yeah, plasma rotating electrode. Yeah, so that's another way of producing these powders, right? So let's keep, oops, am I going in the wrong direction or right? Let's talk about. So you have melted the powder. You have rapidly solidified. You have the powder collected now, right? Which has a very wide size range. Then there are two ways to classify it in the size range that you want, right? Someone wants 50 to 105. Someone else wants 50 to 150, right? So there are ways to classify it. There are two methods. Sieving is the most popular because then you have lot more control over what lower size you want to cut off and what upper size you want to limit it to. Some people also use air classification, right? So for sieving, you normally use it for particles kind of coarser than 10-15 microns, and it has much higher productivity and throughput compared to air classification. And since you are essentially like a chalni type, right? You're using the same thing, so you can very easily get the size ranges that you desire, right? Air classification, yeah. Here 10 to 15 microns is usually the upper size limit rather than the lower size limit, correct? I was trying to get here already with the particle size distribution. There are many ways to do particle size distribution. We will not get into that analysis here, but it's important that for each process that you are targeting and for each material, you should be aware of what particle size distribution is suitable, so that you don't get as someone mentioned, partial melting and therefore heterogeneity in your build, right? I will put a big star against this. So all equipment manufacturers will give recommendations for particle size distributions that are applicable. They will also give recommendation for who you should buy the powder from. Yeah, that recommendation will also come, right? But it is eventually left to our judgment what to do, where to buy these from. Yeah, characteristics, we touched upon this little bit. What are the important characteristics? The one I heard most times is flowability, and that is true, right? I think one of the key characteristics is flowability, which is governed by shape, etc. Generally very fine powders, and when you say fine, you're talking about really fine, yeah, which are not in the regime of AM, right? If you're talking about these days smaller than 10 microns, I think this limit has gone down a little bit, but generally very fine powders behave like talcum powder, right? Little bit. They have too many van der Waals forces or surface effects that tend for them to agglomerate, and therefore those don't flow very well, right? Sometimes density of the material also affects flowability. If the alloy has a higher density, it will flow faster. But imagine that I am mechanically blending two powders. Do you see a problem? If I have mechanically blended powders, right? Or just mix two powders. I am doing functionally graded in DED. I want to do whatever, stainless steel and copper. Yeah. So I've used stainless steel and copper by DED or whatever. Yeah. Both are spherical powders. I have mixed them. Yeah. 90, 10, 80, 20, 70, 30. Do you see a problem because of this? So what I'm looking for the right word. What will happen? Should be low is not your choice, right? If you want to do functionally grading with A and B, you have to live with whatever the density of A and B is, right? That choice you don't have, yeah. But what should you be aware of? You should be aware of segregation, correct? If you are feeding both of them and they are not milled in that sense, but they are just put together, you can get segregation because of differential flowability of each, right, due to density differences. So that's something you must be careful about. In some cases, I don't know, maybe Warangal is a good place, not much humidity in the environment, I hope, yeah. But otherwise, there is often a recommendation that you dry the powder before using, yeah. If you expect that there could be humidity and that can affect flowability or at least lead to unreliable uniform flow, right. So we do this a lot in Sweden sometimes, just dry the powder before we use, right. So don't want to talk about this so much, but I hope this is my last slide. I'm tired of feedstock. I don't like it so much. Yeah. So I think you will see it in your notes, but desirable powder qualities, spherical, no satellites. I strictly don't believe in this. It's okay with satellites. If you know how to deal with them, you can still get very good builds. But this is what today's specification is, right? No satellites, no internal porosity, that's correct. Yeah, few surface pores, because all of these kind of lead to incorporation of pores or defects in your build, right? Narrow size distribution also good porosity, right? So, and I've just put down here how you will characterize these powders. We spoke a little bit about morphology, SCM, etc., porosity. There are different ways to do that. You can, like this gentleman said, you collect it on a carbon tape to look at morphology. You can also mount the powder, yeah, and then look at the cross section to see if there are like particle polishing, and then look at it under the SCM, right, to see if there are pores, etc. There are for flowability, there are very simple devices, right, like a Hall flow meter, where you kind of typically look at how much time does it take for 50 grams of powder to flow, or something like that, right. So there are measures of that, and yeah, little bit on handling, yeah. Surface pores are desirable. Yeah, so desirable is few or no surface pores. Yes, sorry if it is interpreted the other way. I'm not saying few surface pores are desirable. Yeah, desirable is that there should be few or no surface pores. Yeah, correct. Good point. Little bit about handling. These are again, I won't go through all of this stuff, but you should take the normal precautions that one takes in handling powders, right? Especially when you go to finer powders. Some of these powders can be airborne, and if there is a possibility, it's not so much of a problem in PBF, because most of it is done in an enclosed chamber. But when you are dealing with DED, etc., you should be careful, especially if there are possibilities of fuming, and therefore getting some sort of nanoscale material formation, right. That's something you should be very careful about. Good to wear masks, yeah, but otherwise these are very normal procedures that one adopts in dealing with powders. It's good to know that all of those precautions apply, yeah, as you can imagine. I mean, there are various steps during the AM process where You just don't want to stand there and do that kind of stuff. You have to do it in an enclosed environment, right? Where proper protective masks, do it in a well ventilated environment and stuff like that. A little bit about reuse. We spoke about that very briefly yesterday. Not so much from a safety and health point of view, but from an ecological standpoint, always good to try and be very aware of potential for reuse of these powders for various reasons, because these are all very expensive feedstock, right? So you don't want to use it once and throw. You can use it several times. And they are, depending upon application, capable of being used many, many times, right? I am showing you here an image from some of our work where we have used Ti6-4 almost 70 times, right? Here I am showing you only the morphology here. You see, this is how you start, because the supplier is recommending spherical powder, no satellites. Here the sphericity is retained. You see some, I apologize for this bad micrograph, but you see some satellites coming up on these powders, but it can still be used. It of course has slightly higher oxygen content in the powder, right? But that is little bit application specific. If this was stainless steel, then I would use it several times, doesn't matter, because the applications of stainless steel are also little bit more forgiving. So you must relate potential for reuse and how many times, because oxygen content will progressively increase. That is known, yeah. So you must relate this to your application in a good way, yeah. Waste disposal, also for good housekeeping again. You cannot just take the remaining powder and throw it in the garbage. There are proper ways to dispose. You should be aware of what regulations exist around you. In Sweden, we follow this regulation from the EU, which requires both ferrous and non-ferrous materials to be segregated. There is a separate rule if the powder that you want to dispose has been in contact with oil, etc. Then it goes into a different bin, because then it is classified as a sludge, yeah. So at the moment you need not worry about it, right? I'm just saying that these are the kind of things you should be aware of depending upon what you are using, right? Can't throw it in the sink or in your garbage dump. That is important, right? Let's talk about little bit wires and then get on to something more interesting. Powder versus wire. I didn't go into much detail yesterday, but wires are often a more economical choice. We've seen that all the biggest AM structures that have come out of our work have been in case of wire DED, yeah, rather than powder, yeah. So wires can give much economical output in that sense. It also gives a higher deposition rate compared to most other methods, and one handicap, however, is with a wire you can't make parts that are as complex as one can make with a powder, right? So that's one of the handicaps. Also, we just spoke about safety. Most of these issues don't apply when you're using powders, but much safer to handle. Today, and things can change tomorrow, but today the wires that we use in DED are same as what wires we have been using for welding, right? There's not much difference. And when I say wire, I am using it kind of generically. Today people use solid wires, hollow wires, metal core wires, flux core wires, all of these can be used just as they are being used in welding, right? Uh, Drawing or rolling are the, like we spoke about atomization, drawing and rolling are the most common methods of making these wires. They are usually cold drawn. In some cases, you need an annealing step, not always, but sometimes after cold drawing, you may need some annealing so that you restore the ductility. That's true in case like titanium, for example. Uh, People resort to warm drawing as well. And when you're talking about cold wires, there are different ways to prepare that. But the guys in AM need not worry so much about that. Yeah, it's available. You use it. Yeah, and there are many people who know how to make these wires. No problem. Uh, Again, today I emphasize that all the time. At least at the moment, the AWS and ISO codes apply for all these wires that you would want to use in AM. Yes, please. Hmm. You're saying wire spool has got contaminated. I don't know. I mean, you should not let, but you raise a good point. I don't know where it is, but uh, maybe I ran out of space. But that's exactly the point I wanted to make on this slide, that especially in AM, etc., storage of these spools, etc., will slowly become critical. Right now, people don't worry about it for welding, but uh, it will change, yeah, uh, for AM for sure. So, I don't think you can revive that spool in some way. I mean, you must use it for applications that will accept the kind of damage that has happened. I think that is the best thing that I can tell. But otherwise, you can't do so much. And even if you are able to do something, it will be much more expensive than buying a new spool. I guarantee you that, right? So it's not a good or simple way to take care of it, right? Uh, So, as I said, at the moment we are using wires that people use for welding, right? As you know, in welding and cladding, dilution is a big issue. Yeah, so people correct uh, for uh, for that kind of stuff. They compensate for it for this kind of dilution in the wire composition, right? You may not need that in case of AM, because when you are building large structures, the dilution is limited to the first few layers. After that, there is no dilution, right? So you may not need the kind of correction that you incorporate in these wires in case of welding and cladding. So that's important. The other thing to remember is times there is a probability of accumulating elements like oxygen and nitrogen, yeah, with increasing number of passes, right? Uh, so this will be even more critical in case of AM, because when you build higher parts, I mean larger parts, you can get more and more accumulation of oxygen and nitrogen. So I think even purity, when it comes to high performance materials like titanium alloys, that's also something you will need to pay attention to, right? But at the moment, standards, regulations, even suppliers of traditional welding and cladding wires are being looked at by the AM community as well. Yeah, and there is, of course, a very large portfolio of such wires that is available, right? Just a summary of what I said. Uh, Powders produced for welding also used in AM, and this is a caution, but that may change tomorrow. As AM technology evolves, you will perhaps have some specific modifications that become necessary in few alloy systems like titanium nickel based superalloys. Uh, And exactly the point that you made, I was looking for it on the earlier slide, but storage of AM wires will require extra caution, and that's exactly what I meant, right? When you look at much larger structures, I think any impurity uptake or even things like oxygen and nitrogen, which we tend to not attach much importance to, could become very critical in case of AM builds, right? So, nobody talks about it today, but I think this could become important at some point, yeah? I want to stop here on this one, move on to post treatment, but is it time for a break or I can start?